All right, thank you. So thanks to the organizers for putting together such a great meeting. I've enjoyed all the talks so far. I'm going to kind of change gears a little bit and talk about more of kind of a physics-based look at the world, and the way that I've been thinking a lot about fire in the last few years because of some of the changes that we've seen in the world as a result of changing climatic conditions. And so I think that, we oftentimes think about feedbacks between the climate system and forest ecosystems and disturbance regimes, right? And there's been a lot of work on, for example, the relationship or effects of the climate on forests and vice versa, right? So the forest's job in regulating the climate system. Same with the starting in about 2006 with Leroy Westerling's science paper, where he did the attribution work between temperature and area burned, right, or the number of fires in that top panel, and showed that in years when the temperature was higher, there was much higher frequency of fire. And then the interesting part in my mind, though, is really the mechanism. So the earlier spring snow melt in that middle panel. And so really what's happening is temperature goes up. We just see an increasingly large fraction of the year where the fuel, the forest, is available for combustion. And so, that was some of the first attribution work. And where I live in the southwestern United States, our fire season length has increased by about 70 days in the last 4 decades. So, an increasingly large fraction of the year, we've become flammable. And then in 2016, John Abatsoglu and Park Williams published this paper where they looked at the relationship between fuel aridity and forest area burned in the Western United States. And, basically what they found is a strong positive relationship between how dry the fuel is and how much forest area burns. And then they were able to attribute half of that burned area to climate change. So basically the warmer, drier atmosphere is responsible for conditioning those fuels and accounting for half of the area burned over that period. I think interestingly about this data set is that, their analysis ended in 2015 and they were still able to do that attribution work. And, that doesn't include the last 7 years where we had some pretty remarkable fire seasons in the Western US. So, and then earlier this year, we published this paper. Carolyn Wong from Park Williams student led this effort where we looked at, all of the forest fire area across the West and looked at relationships between it and vapor pressure deficit or atmospheric dryness, and then evaluated that relationship over the range of atmospheric dryness conditions we had in the record from 1984 to 2020. And what we found is that, rather than a linear relationship, we've got an exponential relationship. So having an exponential model explained a lot more of the variability in that system. And so, that's really important for the way that we think about fire, because a lot of the tools, a lot of the models we've developed and stuff like that were developed in a linear part of the system, right? So the climate system from 20 to 30 years ago, when a lot of our models were developed, the response of fire to the climatic system was pretty linear. It was quite predictable, and and then all these tools are then applied now when we're in a very much a non-linear part of the system. And we're seeing responses that are consistently not conforming to our model predictions, right? And that's problematic for a variety of reasons. One of the things, if you look at fire spread models and the like, is that a lot of them don't include the fuel that's in large dead trees standing and on the ground, right? We've got increasing climate-driven tree mortality. So we've got a lot more biomass available in the dead carbon pool or the dead biomass pool to fuel these fires. And then the increasing atmospheric water demand or atmospheric dryness is conditioning these fuels to burn. And so we've got a lot of work to do to really understand how this nonlinear part of the system is going to behave so that we can, develop new equations to predict these responses. And I think this is, really important for a variety of reasons. But one of which is in my home state of New Mexico, we had a prescribed fire lit this spring that ended up burning, a significant land area and a bunch of communities because the system didn't respond the way the models said it would. And so how my thinking on this really changed in September of 2020. And so this map on the left, you can kind of see the outline of the Creek Fire in the southern Sierra Nevada and California. And it wasn't an especially large fire. It was maybe only 120, 130,000 hectares. But this area right down here in the lower right is the Tea Kettle Experimental Forest. And I've been working there for 20 years. So I have a lot of attachment to this landscape and a lot of experience working in it. And like all of you, I'm sure I was sitting behind my screen in the September of 2020 because we were all stuck in our houses. It had been an exceptionally warm year. This fire event came on the heels of the severe drought from 2012 to 2016, and that with lots of tree mortality. So we had lower elevation, we had say 90% tree mortality, and at the mid and higher elevations, we had as much as 30 or 40% tree mortality. So that there was a big transfer of biomass from live to dead pools. And then, this map of daily fire growth shows the first few days of the fire. And this big red patch right here is 1 day spread of a little over 40,000 hectares. And, I remember watching the VIIRS sensor pass over and seeing this huge explosion in fire growth. And then the news reports. And so the fire was pushed across a canyon. It jumped a reservoir, right, and trapped a bunch of people around this giant reservoir. And so, we were seeing fire behavior that up until that point, I thought we had been doing a good job of modeling, because we're like, oh yeah, our models show this around 2050, 2060 when we project. But here we are in 2020 and we were seeing the system behave in this way. And so, the other thing that was striking about this is every day I would get up and I would look for the VIIRS overpass so I could see how much energy was being released from the fire. And, inside this big red patch, for several days after the flaming front passed, we were seeing an energy signature that looked like it was the flaming front. So there was a huge amount of combustion happening in the interior of the fire. And that was, that's problematic for a variety of reasons. But basically this fire was releasing so much energy to the atmosphere. It had a plume that was, way in the upper atmosphere, and it was creating its own weather patterns, it was not windy at that time, but it was generating like extreme winds and everything like that. And so pretty remarkable fire behavior. And so anyway, it was at that moment that it became clear to me that we needed to make some changes in the way we were thinking about this system. And so Marissa Goodwin, who is in my lab, and I started talking about the ways that we could evaluate what exactly was happening in the system. And at the same time that the Creek Fire was happening, the Cameron Peak Fire in Colorado in the Rocky Mountains occurred. And it too exhibited very extreme behavior because it burned through a lot of dead trees. It blew over the Continental Divide, which is, rock and snow and, tundra, alpine tundra. And so, pretty extreme fire behavior. So Marissa and I took the U.S. Forest Service inventory data for both of those regions and looked at the plots are measured every decade. And so we looked at, before known beetle events, what did the dead biomass look like? And afterward, what did it look like? And then plotted, where did my, that's interesting. Okay, well, for some reason, the data points have disappeared from this slide. But what you would see if the data points were on the slide is that you would see this shift toward, this area right here in both. So there was a lot more dead basal area 10 years, after the beetle outbreak, which of course is painfully obvious when you walk through the forest. But the interesting thing was basically thinking about that as stored energy on the landscape that's now available for release. And so this series of panels were all calculations we made for and data for the Sierra site. But basically we looked at how much more of that, those big woody fuels were available to burn under the 2020 conditions versus would have been available to burn in the past. And basically, you can see in this first panel that dotted line is the 2020 temperature in the summer. So it was considerably higher than the period. The earliest period we had, that blue line, is the late 1990s, so 1998 to 2002. And so big jump in temperature. Fuel moisture content was a lot lower. So with these big coarse fuels, the kind of rule of thumb is that if you've got 30% fuel moisture or higher, they're not really available to burn. And you can see we pushed well below that early in the season. So in April, we were below that, and we peaked, in May, and then we spent the rest of the fire season with that biomass available to burn. Fire radiative energy, so a huge amount of energy available in that region for release. And then basically, if you get out to where the creek fire started, we had about 87% of the biomass in these big dead logs and snags was available for combustion. So a huge amount of energy waiting to be released on the landscape. And so Scott Stevens and some other colleagues evaluated the typical tools, the like flam map and stuff like that we use to model fire, and found that they failed miserably for this type of mass fire event because there was so much energy being released on the landscape. And I think this is pretty important because Mark Finney, who's one of the co-authors here, he's the one responsible for designing most of these operational fuel models, right? So, and Mark has known like the system is changing, but the basic fact is that all the tools that we've developed to model this sort of thing are failing miserably because of changes in the physics of the system. So, there are other fire models being developed, like this one fire tech from Los Alamos National Lab that my colleague Rod Lynn is developing. And Rod is a physicist by training, so this uses a coupled atmosphere-biosphere model, and it models fire spread using fluid dynamics. And so it's great for thinking about how air flows through vegetation and how it pushes fire through vegetation, but again, not capable of dealing with this huge increase in biomass that we're seeing occur for combustion. And so, I think that this is one of those talks where I'll probably leave you with more questions than answers, because I'm at that point in my career where I have more questions than I do answers. But when we look at this recent analysis by Bill Hammond, he built on what Craig Allen had started maybe 12 years ago and cataloging all of the tree mortality events around the planet. And, these are all hot drought kind of tree mortality events. So vapor pressure deficit spikes, conductive, the catastrophic conductive tissue failure in the xylem, and tree mortality. And if you think about how much more of the biomass is transitioning from the live to the dead pool and then available to burn, we're going to end up with a lot more fuel on the landscape. And we have to figure out how to predict what fire will do both in terms of the way it behaves with vegetation and then also what it's going to do to the ecosystem. And with that, I'm happy to take any questions. And I think, yeah, 15 minutes. There we go.
Thank you, Matt.
Yeah.
Is there any questions for this presentation?
Adam.
Do you think has Westerling finding that the condition during the spring will also play a key role for the future? And what's your feeling about it? Notably about this quantity of water in the ecosystem below and also in the streets.
Yeah. So I think if I'm going to connect the dots from Leroy's work to what we've been doing, it's that that basically in the past, snow melt happened late enough into the spring where it bought us a good deal of time into the fire season where these big coarse fuels were not available for combustion because they had so much water stored in them. And it's basically that whole period, though, is shifted earlier in the year. And so what used to be a phenomenon that would occur in August is now occurring in April, you know? And so it's basically like, I mean, I think last year, what did we spend? The US government spent like $3 or $4 billion on fire suppression, and the state of California spent $1 or $2 billion just in California on fire suppression. And basically, like, what's happening is it used to be that, you know, for California, the northern part burned and then the fire season ended and then Southern California started burning. And now it just kind of burns all year long, you know, because it's warmer and drier year round. Yep. Yeah.
So, does fire suppression work?
98% of the time. But it's the 2% of the fires that escape initial attack that do all of the burning. So yeah, it's really effective if you catch it right out of the gate. But I think we've learned in the US that no matter how much money we spend, I mean, we can paper the landscape with money and it's not going to stop all the fires because money burns too. Yeah, Igor.
Thanks. Very nice presentation.
Thank you.
Like this, I want to touch upon this modeling approaches because clearly we always have some kind of a trade-off between how complex the model is and how happy you are by extrapolating the results over larger areas, sometimes into the areas where hardly have like really solid data. You have some kind of inventory data 20 years ago or 10 years ago. So I wonder if you think there is some kind of solution in finding this trade-off between complexity of the modeling exercise and the actual benefit of this modeling exercise.
Yeah, that's a great question. And I think in order to make whatever we come up with operational so that, you know, a fire manager can use it, it has to be something that you can run on a laptop, right? You can't require a supercomputer and, you know, 72 hours of computational time to run a simulation when you're planning a burn. And so I think that we need to do some more experimental work in the field where we actually manipulate fuel moisture and air temperature. And because I think my hypothesis is that if we have a good understanding of the relationship between soil moisture and fuel dryness, and then, you know, atmospheric dryness and fuel dryness, those two things, they should be enough that we can make a reasonable prediction about how the system will respond over short time windows. Yeah.
How important are the different types of fuels? You were saying that lots of the burnt energy is coming from the log fuel actually inside there, which of course releases a lot of energy inside there. Then what I'm, as a boreal scientist, I'm of course worried about what's happening in the deeper layers of the humus inside there. So
yeah.
How important, how much do you see changes there between really surface fires like in the picture there and then the big fires which go deeper into the ground actually?
Yeah. Yeah, I think the so the fine fuels that we're burning here and up to stuff like as big around as your arm, right? that stuff is available to burn most fire seasons. I would say even in a typical late season, even in the boreal zone, that stuff is usually dry enough to burn, right? And so I think with the big coarse wood where we are, it was available to burn very infrequently in the past, and it's gotten more common. I think the same thing is happening with the organic layer when I read about a lot of the work done in the boreal in terms of fire, just the fraction of the organic layer that's drying out with increasing regularity, making it available to burn. And then worse yet is that when part of it burns off, kind of the feedback and how much more flammable the next layer is on the next go around. I think that it's similar to the wetter, colder systems at lower latitude, where it's just with increasing frequency, we're seeing the system become much more flammable than it has been in the past.
Time for one more. Aside from prescribed burnings, what kind of fire management is done based on those models?
So the model where Scott and colleagues modeled the creek fire, that's the same model they use to plan suppression. And so you can imagine if your tool for figuring out where you're going to put people and aircraft and things like that is failing, that's not good, right? So you're increasingly dependent on, when I talk to my friends who work in fire suppression, what they do is that they're basically, they go up in a helicopter or an airplane and they're looking down, and then they have they have their kind of expected frame of reference, for what they expect the fire to grow based on their past experience. And then they're just they're going back even further because it's not safe to be surprised when you put people on the ground, right? And so, to compensate for the fact that the tools are not good at forecasting fire spread, they're just drawing a larger and larger box around the fire, and increasingly that box in the lower 48 states includes a bunch of houses, because they're having to pull back far enough that, that you draw a circle around a neighborhood and go, there's nothing we can do. Thank you.